Next, we are going to be talking about discriminant analysis. So what's the big idea? The whole point behind discriminant analysis is to find a method where we can use dimension reduction, plot the data on new dimensions, and then use that to draw a line or boundary to separate our classes. So remember, the whole point behind discriminant analysis is the prediction of group membership. It still creates kind of an equation, but the goal is now going to be group membership as opposed to finding a linear relationship, which is what we did with multiple linear regression. So if you remember, in multiple linear regression, we had the y, which is our predicted variable, and then we had a variety of independent variables. In discriminant analysis, instead of trying to build an equation that predicts y, we are trying to build a discriminant function where we have weighted scores because not everything is equal. And then we're going to try to figure out which predictor or independent variables do the best job of helping us to assign things to categorical groups. One thing to keep in mind is in this presentation, capital D is going to represent the score on a discriminant function, whereas a lowercase d will correspond to Cohen's d in reference to effect size. So the term weighted refers to the fact that each variable is multiplied by a coefficient. The whole idea of weighting is to have some measure of importance in that model. Variables with larger weights or coefficients make larger contributions to the total value of the composite when compared to variables with smaller weights. The term linear implies that the multiple regression function is a computation that involves only addition, subtraction, multiplication, or division by constants. And then finally, the term composite refers to the fact that all of the variables are combined to create a final model. The goal of multiple regression is to build a weighted linear composite of raw scores, or the x values, which are my independent variables. Or we can do the combination using standardized z-scores of the variables, and then we look at the slopes. So we have all of those weights together, and those become the coefficients or the slopes. This goes into more into why we use weighted linear composite and multiple regression. Again, it really is a function of the importance of each of those variables in your final regression equation. So not all things are going to be created equal. Another thing to think about is that if I do not standardize them, different independent variables will perhaps have different units of measure, and if they're not standardized. So that even the effects of the weighting on them and how they are used in your equation. So if you use the raw values, it's not going to be surprising that you have different weights based on the importance of the model, the measurement scale, the range, the standard deviation of that particular variable, and so forth. So all of those things come into play when we are looking at those independent variables. In an example of linear composite, we want a summary measure of socioeconomic status with predictor variables being annual income in dollars, occupational prestige rating, and years of education. However, before you combine these variables, you will need to convert these values to a standardized value so that each of them are weighted equally in the linear composite model, with the linear composite model being z sub 1 plus z sub 2 plus z. Sometimes you don't want the variables to be weighted equally. Perhaps you wanted the prediction of socioeconomic status to be used as an index of success in life. How would you weight the variables differently in this list? Since those values may be more difficult to assess, these multiple regression and these weighted linear combinations is where we are trying to assess that. So it is a function of understanding the importance of each of those values in predicting y. Where when we come to discriminant analysis, it works just a little bit differently. So we are going to create new variables, and those are a function of our discriminant function scores. For instance, here we have our discriminant function d sub 1, where we have the z value for the associated variables, and we want to use the coefficient, which then becomes essentially their weight. Both types of analysis results in equations based on weighted combinations of raw scores or standardized scores of the X predictor variables. So they both use a weighting factor, meaning that some variables are going to be more important than others when they make predictions about the outcome variable for each case. Like multiple linear regression, discriminant analysis uses optimal linear combinations of predictor variables to predict and explain the outcomes. In multiple regression, we are trying to predict a score for Y. So for example, I might want to predict income for 10 years based on these factors. Or I want to predict how many jobs you will have had based on several variables. In discriminant analysis, we are trying to predict a group where they belong. So we're going to predict scores on one or more functions that have means as far apart from each other as possible. In discriminant analysis, we are going to look at the within group and the between group values. So it is about strengthening your within group and then having more distance to the outside, so that the groupings seem to be unique and distinct so that we can maximize the overlap between the groups as much as possible. When you perform a multiple regression, you are going to have one predictive equation for Y prime. Additionally, Y prime will be a continuous variable. However, in discriminant analysis, the number of discriminant functions that are created in discriminant analysis depend on the number of groups and predictor variables. These functions are using continuous variables to predict a categorical variable. The number of functions in a discriminant analysis will be the smaller of the two values between the number of groups minus 1 and the number of predictors. Really, the number of groups is a function of what you're trying to do. How precise do your groups need to be? Sometimes it's a function of how big your data set is. We'll talk about sample size and effect size later on, but how do you know how big your sample size needs to be so that you can do an analysis that ends up being statistically significant for your output? The number of groups that you have truly does impact what the equation looks like. So again, more differences between multiple regression and discriminant analysis is the computation of the coefficients, and the goodness of predictions in discriminant analysis can be assessed in several ways. There are several subtests that we look at to help us to decide how we're going to interpret the output that we decide to use and which one to use. So when we look at overall significance, when we're looking at multiple regression, we are typically using the F ratio. So that is based on the MS regression divided by the MS residual. So we are looking at the goodness of fit by looking at R and R squared. Those are things that we are used to looking at. They should make a lot of sense to us. R squared is our variance explained. So how much of the variance in your outcome variable is explained by the variance by your predictor variables. So when R is large, we have a stronger model. R squared is large, we have a stronger model. In discriminant analysis, the goodness of prediction can be evaluated several ways. For each model individually or separately for each discriminant model. So the individual models can be evaluated by the eigenvalue and canonical correlation, and sets of functions are evaluated by using Wilks lambda. So there are several ways in which we can decide if, in fact, the discriminant analysis that we have has met our requirements and is statistically sound and statistically significant. You may want to consider completing a discriminant analysis if you want to develop a model to predict group membership for individuals. For example, who are the people who would be best fit for a job? Or who would be, for example, who would be the best firefighters, teachers, or business people? You may want to be able to describe the differences between the groups. So maybe it's not just about assigning things to a group, but the differences as well. So maybe people who are good firefighters maybe have a lower fear factor. Maybe business people tend to be more bookish, analytical thinking, and more averse to physical risk. Maybe our teachers are somewhere in between. Discriminant analysis of two or more groups can be conducted for one of several purposes, including visualization of groups and to try to separate them. So it's more of a visualization to see how groups separate. Another one is to identify a subset of variables that separate the groups. Another one could be the interpretation of new axes as defined by our discriminant functions, and we'll see what that looks like here in a few minutes. And then it can also be an extension of other multivariate analyses as well. So for example, you could use cluster analysis on the predictors to determine how many groups there are, and then you could use discriminant analysis to further understand the group differences. And so ultimately, the way to think about this is we can start with data in groups, such as default or not default, and then we can do all these types of things with that type of information. We can visualize it to identify subsets of variables that separate groups, or we could do extensions of other multivariate analysis. So let's look at an example here to draw more of a concrete understanding of what we are doing from this analysis. And to do that, let's revisit what we were doing with univariate analysis of variance. If you recall, when we are looking at an ANOVA, we are looking at the distributions to see if there are differences across the groups. If you can assume normality and a constant variance, then we can evaluate the differences in the means, so we test to see whether there is a difference in the means by using the F ratio that evaluates the between data variability and then the within data variability. And then we can make an inference on whether or not the means were different. Now we can extend that to a multivariate view. So this is looking at now 3 dimensions. And with more responses, we still want to separate the groups and look at that between variability as well as the within variability. And that is what we are doing. We're looking at that distances between each group centroid to the overall centroid and the distances of each response to the group centroid. So we are applying a similar technique by applying discriminant analysis, which effectively is a test or a multivariate analysis of variance. So how does it go about doing that? So let's review that. Discriminant analysis starts with the assumption that there are different groups, and the discriminant functions use continuous variables to calculate the how to best separate the groups, and the discriminant functions are linear combinations of the data, which is very similar to principal components analysis, where principal components are linear combinations of the data. So, linear discriminant analysis classifies observations based on the distance of an observation from each of the class averages and can be thought of as a classification rule that separates a two-dimensional region into 2 parts. The linear discriminant functions are combinations of continuous data, and these linear combinations can be used to predict groups when the group members are not known. But just to be clear, this is not the same as cluster analysis. In discriminant analysis, the discriminant function can be thought of as the best possible linear combination of the X predictor variables that maximize the squared distance of the overall centroids of the data. So here is a visual of what we are doing with discriminant analysis. Here we have X1, X2, and we have a line that separates these 2 groups. We'll talk about in a second how we go about computing this line that will separate these 2 groups in the most optimal way. But in its most simplistic term, what we are doing here is we're drawing a line that is going to best separate the 2 groups from each other. As I mentioned, there are a few goals, and the 2 primary goals that we will use discriminant analysis for is first for discrimination. That is, how are the groups different? Okay, and you find and interpret them, and then your combination of the variables that optimally predict the differences between the groups. The other thing we use it for is classification. which looks at how accurately we can classify objects into groups, and we use functions of variables to predict group membership for a data set and evaluate the expected error rates. So let's look at the discrimination case first. Here what we are doing again is compiling a linear combination of all of our x variables. And we are constructing a line that is going to maximize that scaled squared distance between the means of the samples. That is what's going on mathematically. And so here we are computing the line that separates the two groups using this method. So here the y's that we are calculating are the scores. And what you are seeing here visually is if you were to extend the line, then draw a perpendicular line that goes through the origin and onto that line, you would draw the two normal distributions of each of the centroids. The mean of those normal distributions are going to be the projections of the centroids on the line that is separated as much as possible. But again, the gist of it is, here is the line that we are fitting, and it's just maximizing this scale, the squared distance between the means of the samples. So it is leading to the best discrimination between these two classes. So what would happen if you had if you had more than two groups? You could extend this mathematically, and here you could start seeing what this looks like when you have more than two populations. So again, you can extend this further and look at multiple groups. We're not going to do that though, but the mathematics are there just so that you see that you're essentially doing the same thing but in a higher dimensional space. And so again, you start using a lot more matrix algebra to try and find these spaces in multi-dimensional space that will then minimize or create the best separation in your groups. So now let's go into the probability of classification. So here the linear discriminant functions score the observations on their similarity to the group centroids. Observations are assigned to the class that gives the highest score, and the scores are then computed to the probability of the group membership in each group. And this enables error rates and the training data, and then enables predictions for future data that we may want to classify. One of the outputs from JUMP that we would be able to see is the canonical plot, where you plot the scores on the transformed axis. So we have canonical 1, which you can think of as similar to a principal component or a factor, but it's not exactly because it uses a different algorithm. So it is a dimension reduction approach again. This is one dimension in red, and then the second dimension is in blue. And so we then see that we're plotting these observations with the centroids of our two groups indicated with the black crosses. When the covariance cannot be assumed to be the same across groups, which again is one of the requirements when you're using linear discriminant analysis, then you might want to consider using quadratic discriminant analysis, which uses a separate covariance matrix for each group and small sample sizes. Many variables can mean problems with the estimation of each covariance matrix, so you have to be careful if you have a small sample size. This might not be a good approach for that problem. Now, should you use linear or quadratic discriminant analysis? Linear discriminant analysis is much less flexible than quadratic discriminant analysis, so it will have a lower variance. And then linear discriminant analysis can lead to poor estimates of the boundary between the groups, which means it will have high bias. If the sample size of the training set is high enough to support estimation of separation or variance matrices, then quadratic discrimination is going to be preferred. And then with K groups and P variables, the number of covariances to be estimated is going to be determined using this function that you see here, which is K times P plus 1 divided by 2. We will need a minimum of 20 to 30 observations to estimate one correlation. So if you had an example with 3 groups and K equals 3, and you had 4 variables, then you would need approximately 600 or more observations to be able to compute this. That is determined from 20 times 3 times 4 times 5 divided by 2. That's 600 observations. So you would need a minimum of 600 observations for that type of classification problem. Similar to other algorithms, you can also apply regularization to the discriminant analysis, and regularized discriminant analysis is a compromise between linear and quadratic that blends the pooled covariance between the individual covariance matrices. And so that is what we're seeing here. It's controlled by this lambda, where lambda equals 1, it is linear, and when lambda equals 0, it's going to be quadratic. So you're going to do a mix of the two, and it deflates the off-diagonal elements. And so again, you can see how this is done here. And the choice of the lambda that we use of the two metrics that we use to tune the model are going to be determined using a holdout test set. So that would be the one that maximizes the accuracy for that holdout test set. But again, we can pull the two and we can deflate the off-diagonal elements using these two parameters, which again, we will determine using a holdout test set. Now, what are the assumptions used for interference? And again, this is important to note, as we have talked about before. When you're applying it for prediction purposes, then the assumptions are not relevant. But if we are making an inference from these results, then making sure that we adhere to the assumptions will be critical. So the assumptions that the predictors are approximately from multivariate normal distribution. You are assuming equality of variance, covariance matrices, so they've got to be the same. And there are not any singularities or multicollinearity. So you cannot have perfect multicollinearity or perfect collinearity. And the consequences of unequal group dispersions mean that you have invalid significance tests, and then your linear canonical functions become distorted, and you'll have biased estimates of the canonical parameters, and then you will also have distorted representation of the entities in the canonical space. So although these assumptions can be violated in practice, this method is surprisingly robust to these violations. But there are, in fact, the actual assumptions underlying the approach when using this for inference. But in practice, you're going to have some level of violation of these, and the method is fairly robust to the small violations of these assumptions. And again, you do not need to meet these assumptions when you're using this for prediction purposes. So let's transition forward to classification. Here we are looking at how actually the observations can be classified into groups. And here we use a discriminant function to classify new observations. So new data are scored using the discriminant functions that are generated, and then group membership is predicted based on the scores of the new observations. And looking at the prior probability estimates in discriminant analysis, it may actually be useful to specify your prior probabilities. By using prior probabilities, you can specify how to estimate the probability of the group's membership in the population. And then your priors can be equal probabilities proportional to occurrence or user specified. Now let's talk about how we go about doing an assessment of your model. Similar to other algorithms, you're going to want to validate your model, and it's going to be particularly important for linear or quadratic discriminant analysis. This is because discriminant analysis can capitalize on chance associations in the data. So if there are spurious or correlations, that's going to get picked up, and it's going to be included with the actual function that's generated. So we want to make sure that we test for that. And then you apply the equation to a new data set to get a better estimate of the expected misclassification rate for the population. We do that by using holdout validation. So if a new data set is not available, then we will randomly select a training data set and a test data set so that we can assess the predictive capability on the test data set. And again, just as a reminder, The test data set or validation data set is not used to build the model. And in this case, we will then use that to validate the overall model. In some problems and in some cases, you may actually have 3 splits of the data. So you can have your training set, which you use to train your model, a validation data set, which you use to tune your model, and a test data set to validate that it generalizes well and that it is not overfitting. As for the advantages and disadvantages of discriminant analysis, among the advantages are that it is easy to implement and it leads to a very fast classification. It tends to generally perform better than other algorithms such as logistic regression. And again, that is when the assumptions are being met. And then the quadratic discriminant analysis is much more accurate than a linear discriminant analysis because you have higher flexibility and you can draw some different boundaries other than just a linear separation. So if you can try to use the quadratic discriminant analysis, but you're going to need more observations to do it, so make sure you have plenty of observations. Among the disadvantages, you need to abide by the Gaussian assumptions that underlie this algorithm. And so you have to have a high training time, and it does take quite a bit of time to train if you have a very large data set. And it does have complex matrix operations, which is why it takes quite a bit of time to train. So those are the drawbacks, but overall, discriminant analysis is a very effective method to use for classification.